Hey everyone and welcome to my talk on algorithm selection on a meta level. My name is Alexander Tornede from Paderborn University in Germany, and this is joint work with Lukas Gehring and Tanja Tornede, also from Paderborn University in Germany, and Marcel Wefer and Eike Hüllermeier from LMU Munich, also in Germany. Since this is a journal track of the AutoML conference, this work was published first in Machine Learning by Springer in April 2022. Okay, so let's dive right into and discuss the algorithm selection problem. The AS problem was first introduced by Rice quite a while back ago in 1967, and the general idea is that you have a set of instances of an algorithmic problem, such as, for example, the Boolean satisfiability problem, the traveling salesperson problem, or even just classification in machine learning. And then you also have a set of heterogeneous algorithms, heterogeneous in the sense that they can solve these instances differently well. So, for example, algorithm A1 might take longer to solve instance I1. And then what you try to do is you learn a mapping from the instance space to the set of algorithms, such that for a given instance, we always try to choose the algorithm which is optimal with respect to some measure m that just maps from the joint space of the instances and the algorithms to the real numbers. And this measure could be potentially anything. For example, it could be runtime if you try to solve SAT instances, but it could also be accuracy in the case of classification. Now, how do you solve the algorithm selection problem? Well, the easiest solution that, of course, comes to mind is that when we're given an instance I, we simply select the algorithm that works best according to M, because that would, of course, give us the optimal solution. So we essentially do an exhaustive enumeration over the set of algorithms. Unfortunately, that doesn't work because this measure M is usually costly to evaluate. For example, think about the case of runtime. Of course, it doesn't make sense to run all of the algorithms because by the time you know which one is the fastest, you have already run all the algorithms anyway and your instance is solved, so you haven't really gained anything. That's why the real solution is slightly different. What most approaches try to do in one way or the other is to try to learn a surrogate M hat of the original measure M, which has the same signature, however, now has the property that it's actually cheap to evaluate. And once we have this property, we can do exactly what wasn't possible before, namely the exhaustive enumeration over the set of algorithms, and then just select the algorithm that, according to the surrogate, will perform best on the instance. And in order to learn such a surrogate, we usually represent the instances by features. These features could be anything. For example, in the case of SAT, it could be the number of clauses or the number of variables. The only property that is extremely important is that it somehow need to be correlated with the performance of one or potentially all of the algorithms on the instance. Now, since the problem is around for quite a while already, there exists a large set of existing solutions, or more precisely algorithm selectors, here denoted as large S, which also, in fact, feature performance complementarity in the sense that on some instances, some selector makes a better recommendation. And then, of course, two important questions come to mind. First, why don't we just instance specifically choose among these algorithm selectors? And in fact, why do we actually choose one of the selectors at all and not just combine multiple selectors, or more precisely their suggestions, in order to come up with a hopefully better suggestion? Now, and this is exactly what meta-algorithm selection is about. So here you see basically the same picture as you saw on the first slide, but now in the meta-algorithm selection problem, instead of seeking to learn such a direct mapping from the instance space to the set of algorithms, we actually take what I call a detour. And the detour looks as follows. We learn an ASS, short form for algorithm selector that maps from the instance space to the power set of the possible selectors that we have or that are available. And then from these selectors, we actually can aggregate, namely we actually aggregate either the selectors themselves or more precisely the decisions in order to then at the end have a single algorithm, because of course at the end this is still our target, having the best algorithm for the corresponding instance. So how do we do that? Well, in the paper we propose a couple of different solutions, and the easiest one here is the one at the top, namely meta-learning the algorithm selector. And the idea here simply is that instead of learning the mapping from I to the power set of the selectors, we intentionally say, okay, we just choose a single selector anyway, so the mapping changes such that we only map to the set of selectors. And then you can directly learn this mapping, basically using the same techniques as you would in a normal algorithm selection problem. However, now you choose selectors instead of algorithms and then return whatever they suggest as the final algorithm. And since we only choose a single selector anyway, we also get only a single algorithm, and you don't need any form of aggregation here. But of course, you can also do other things. And this basically answers the second question, namely combining multiple algorithm selectors, or more precisely their suggestions. And this is where the lower two elements of the graphic come into play, namely employing ensemble learning. And we differentiate here between stacking and voting, boosting, and bagging, mainly because in stacking we essentially learn the aggregation, because we basically stack the decisions of the different selectors onto the features that we have anyway, and then learn the final suggestion of the algorithm. Whereas in voting, boosting, and bagging, the aggregation function is basically predefined depending on whatever you want to have here. And it turns out that this direct way at the top doesn't work too well, whereas the ensemble learning techniques actually tend to work extremely well. Now, coming to the evaluation, you see some results here from the paper, namely on the algorithm selection library. And what we're going to look at is normalized par10 values. For those of you who don't remember, the par10 score is depicted at the top right. So the par10 of given runtime, t, is basically t, as long as the runtime is smaller than a certain cutoff times c, or 10 times c if it's larger than that. Now, the normalized par10 score is just normalized to the unit interval, where lower values are better. That's all you have to know for now. What we're looking here is at the boosting ensemble using different base algorithm selectors, which you can see at the bottom, and we see the mean and the median performance across all scenarios. Two important things to note here are that for most of the different selectors, we can actually improve the performance when applying boosting. This doesn't really count for Sunny and Isaac, and the reason for this can be looked up in the paper if you're more interested. And the second important insight here is that for almost all of the approaches, the boosting performance is actually much better than the strongest baseline we have, which is run to survive par10, here denoted as the dashed line. And this is quite an achievement already, because the run to survive par10 is already quite good and achieves extremely competitive algorithm selection results. Now we have a similar graphic here for the voting ensemble, which also performs quite well. However, this time we look at violin plots, which basically show how different compositions of the ensemble employing different algorithm selectors work. The dark dot, so the dark dot is the ensemble composition that you get when you optimize the composition on a different validation data set, whereas the red dot is just the one that the performance of the ensemble containing all of the selectors. And as we can see here, directly optimizing this composition on the validation dataset does not work really well on the test set then. However, if we just take off the selectors anyway, i.e. the red dots, we usually get quite a good performance. And once again, we beat the strong baseline run to survive par10 in all of the cases, independent of the different aggregation function that we use at the bottom. So really nice result. And to summarize, we actually analyzed how many scenarios our strongest ensemble learning approach, in this case boosting, actually wins against all of the SOTA methods, and this is the case for almost half of the scenarios, namely 12 of 25. And we also have a look here on the at the right at the normalized par10 score again of different ensemble approaches, namely the strongest configuration for each of the ensemble approach, once again versus the baseline, once again denoted as the dashed line. And also here we can once again see that except for stacking, we actually improve beyond this baseline, the strong baseline of the cases, which once again is a really strong result. Okay, so to close this presentation, here are 3 take-home messages. First, algorithm selectors feature performance complementarity themselves, and if we exploit this, we can combine multiple selectors in order to actually gain a better performance. And meta-algorithm selection using ensemble learning techniques improves over state-of-the-art algorithm selection approaches, as we have just seen. So if you're interested in this, then have a look at the paper on the left or come by at our poster and feel free to discuss with me. Also, all code is available for free and on GitHub under the QR code on the right. Okay, thanks for your attention and have a nice conference.